Good morning. So, we had from the last lecture we had started the methods of displacement measurement using variation of passive elements like resistance, inductance, and capacitance. And in the last lecture, we had seen resistive potentiometer both for linear displacement and also for rotary displacement. And in this lecture, we would look into variable inductance transducers and also variable displacement transformers like LVDT or RVDT. Now, when you're talking about variable inductance transducers, you basically want to change the inductance of an element in the circuit by means of having some displacement. Okay, and the inductance comes in two flavors. You can change the self inductance or the mutual inductance of the circuit element, okay, by appropriate displacement. So let's look at both of these variations, both of these circuits sequentially. First, let's look at the self-inductance variation. Okay, now before that, let's refresh what is the self-inductance of a coil. So if you have a coil, okay, then the self-inductance is given by n square by r, where n is the number of turns of the coil and r is the reluctance of the magnetic path, magnetic circuit. Okay, and r is again given by L into mu by A, where L is the length of the magnetic circuit, mu is the effective permeability of the circuit, and A is the effective cross-sectional area. And if you remove the permeability, this factor A by L is called as the geometric form factor of this magnetic circuit. Okay, so there is a geometric factor here. There is a factor that is dependent on the permeability of the circuit here, and there is a factor that depends upon the number of turns. Okay, now thus, if you look at it as a whole, the self-inductance of this coil can be written as n square into mu into g. Okay, now there are three factors here, n, mu, and g, and each of them can be used to operate the transducer and to derive the displacement that cause the variation of either n, mu, and g or g. Okay, now let's again look at each of these each of these choices sequentially. Okay, so by varying the number of turns, you can have a self-inductance transducer. Okay, now there is a single coil here and you are trying to measure the output across a portion of the coil. Now this setup is very much similar to the resistance potentiometer. In fact, even if you look at the setup here of an actual variable inductance transducer, it looks very similar to a resistance potentiometer. Okay, and if you are taking the inductance across two of those points, then this N1 is the number of turns between these 2 points, and that is proportional to the effective displacement. However, it should be noted that L is proportional to n square. So what you end up with is the inductance being proportional to the square of the displacement. So this is a non-linear transducer. Okay, the displacement to inductance relationship is going to be nonlinear, and the structure or the construction can be very easily translated from a linear circuit to a rotary circuit. So instead of uh, winding the coil around a core of that looks like a cylinder, you can have a toroidal core, okay, and then wind it, and then again have the wiper mechanism so that you can measure, or you can take the inductance across these two terminals. And so the number of turns here again is proportional to the deflection theta, or this angular displacement theta. Next, we can move on and see the case where you have a variation in the geometry. Okay, so as I said, the variation in geometry factor can be influenced either by changing the length of the path or the area of the path. Okay, so we can change the length of the path by sort of splitting the inductance into two parts and having relative displacement between those two parts. Okay, and but it should be noted that there is a single coil, and the relative displacement between two parts of the coil is going to cause a change in the self-inductance of the coil by changing the effective length of the path, and thus changing effectively the geometry of the path. Okay, so if you have a linear displacement here, that is going to change the length here, and that is effectively changing the inductance L. And similarly here you can have a rotary version of that also, where you have a movable part of the coil and a fixed part of the coil wound around a same iron core, and these two, the movable coil and the fixed coil, are connected in series. However, it should be noted here that the relationship to L from the displacement X or the angular displacement theta, the relationship from this to theta is going to be non-linear. Okay, it's not going to be linear. Even in the simplest case, where even if you see the rectilinear case, that is this one, then what you can assume is the length of the path L is directly proportional to the displacement D. Okay. However, the geometric form factor was A by L. So there is a now of course it has become a nonlinear relationship. Now L, the inductance L, would now have a relationship that is proportional, or even not the actual L, a change in inductance will be proportional to 1 by change in the length. Okay, so that would mean that the relationship is going to be non-linear. And so the variation of geometry, though it's an option, you have to the scale that you would have, from which translates from the displacement to the inductance, is going to be much more complicated than the case where you have the number of turns, which is relative, even though non-linear, it is relatively simpler because you know it is going to be just a quadratic relationship. Moving on, we have a third option of changing the effective permeability of the coil. So if you want to change the permeability, you are changing the material of the core. Okay, but that is not really a feasible option. So what you are changing is the effective permeability of the core by having an iron core, and by moving the coil by moving the core into the field of the coil. What you have here is partially a part of the coil will have the permeability of this iron, and another part of this coil will have a permeability, will be linked with the permeability of air. Okay, and so effectively the permeability will be a linear combination, a weighted linear combination of the permeability of iron and permeability of air. Okay, and that weightage will be proportional to the amount of displacement that is happening. Okay, effectively, as so let us say that this is the positive direction of motion. So as let us say x increases, okay, as x increases, more part of the coil is going to be coupled with an iron core, and therefore the inductance L will also tend to increase. So it's not going from 0, it will be going to be something like this, because the permeability of iron is going to be much greater than the permeability of air. Okay, and you also have another setup, another construction where you have 3 terminals. So here what you have here is that you were employing a shorter core, a shorter former than the case that you have here. Okay, and the advantage that you get is apparent now, because now you have 3 terminals. Okay, you have a null position that is at the center, and you can go in positive direction and also in the negative direction. Okay, and when you go in the positive direction, the Z1 increases and Z2 decreases, and when you go in the negative direction, Z1 decreases and Z2 increases. And the reason for that is now quite obvious, because in either direction, when you, for example, if you go in the Z1 direction, there is more part of this magnetic former that is linked into Z1, and consequently there is less linkage in the Z2 part. Okay, so effectively what is happening is that the inductance of this part is increasing and inductance of this part is decreasing, and so Z1 minus Z2, if you take this as a measurement, this will give you an idea of the displacement x. Okay, and note that now Z1 minus Z2 can be negative or it can also be positive, and hence you can say this, you can sense the direction of motion also, and you may argue that the direction of motion is not really necessary. What you want to measure was the displacement. Okay, and it appears that the displacement could also be measured from here. So you are measuring the displacement of so much of length. Okay, let us say this was L. Okay, here also the length is L only. So what is so great about using this 3-terminal case? The point is that you need to measure a length L, you need only a core of L by 2 here. However, you need a larger magnetic former here. You need a smaller one here. That is one advantage. The second advantage is when there is a displacement of delta L, that causes a change in inductance of, say, delta capital L in the first case. Okay. However, in this case, if there is a displacement of delta L, there is a delta L increase in one of the inductances and a minus delta L change in the other inductance. So effectively, delta L will correspond to 2 delta L. So it is more sensitive. Okay, the 3-terminal setup is more sensitive than the 2-terminal setup. Okay, and similar to the case of the self-inductance, you can also have the displacement measurement using mutual inductance. And just as a refresher, we know that mutual inductance is K times square root of L1 plus L2, L1 times L2, where K is the coupling coefficient. L1 and L2 are the self-inductance of the primary and secondary coils, or not of the two coils between which you want to measure the mutual inductance. Okay, and the change of mutual inductance can be brought by changing the self-inductance of either of the coils or by changing the coupling coefficient. Okay, we already seen the self-inductance part, so we will not go through that. Okay, let's see how the coupling coefficient can be changed. Okay, now here you have two setups. In this setup, by changing the position, by changing the angle here, the coupling is changed. Okay, because in my number of lines, of course, associated will change. Okay, and the coupling changes in a manner that looks like that goes from a maximum M max to as let us say at theta equal to 0. Okay, and it goes to a minimum value of minus M max when theta is 180 degrees. Okay, and then the cycle again repeats. Okay, so that is when both of them are in phase, or when the coils are in phase opposition, you will go from plus M max to minus M max. Okay, and the effective, and if you plan to connect both of these coils and measure the effective inductance, then you would get L1 plus L2 plus 2M or minus 2M, depending upon what you take, whether these two coils are going to be in phase or out of phase when theta equal to 0. Okay, and from that you can determine by measurement of this, you can actually determine the value of M, and from M and its relationship with theta, you can determine the angular displacement. Okay, and in a similar manner, you can use mutual inductance as a means to measure linear displacement or rectilinear displacement. Okay, now here the geometry of the path is again changed. Okay, by having this air gap, by having a displacement change the air gap, and thus change the flux linkages between these two coils. Okay, and thus again affect the overall value of L1 plus overall mutual inductance M. Okay, so it can be used both for rotary angular measurement or for rectilinear displacement measurement. Okay. Okay, proceeding further, we have seen the way that mutual inductance or the self-inductance can be used, okay, when you have electrically coupled circuits. Okay, now on the other hand, the LVDT, or the linear variable differential transformer, is one of the most popular inductive transducer devices, okay, which uses the transformer principle of inductance the transform principle for displacement measurement. Okay, so the construction is like this. It has a single primary and two secondary windings that would be connected in phase opposition to one another, and you have a movable core that changes the coupling coefficient of the primary with each of the secondaries. So the movement of the core in one direction is going to increase the coupling with one of the primaries and simultaneously decrease the coupling with the other primary. Okay, so you can see that you have a core here, you have a primary linked here, and you have a secondary. You have two secondary coils being wound here. Okay, and in a more clear fashion, it can be seen here. Now, if the core changes in one direction, it is going to increase the coupling in one of the secondaries, and it is going to decrease the coupling in another secondary. Okay, this is very similar to the three terminal self inductance case. Okay, however, it should be noted that in the three terminal self inductance case, what you had was you had one coil. Okay, there was no primary or secondary, there was one coil. Here you have a primary which is magnetically coupled with the secondaries. Okay, but there is no electrical coupling between the primary and the secondary. There is only magnetic coupling. Here the way that you measure the displacement is by measuring the inductance, but in this case you don't really measure the inductance at all. You measure the output voltage, and from that infer what the displacement is directly. Okay, and hence it is, and that's why it's using the transformer effect. Though it's major, though it's an inductive transducer, the measurement of inductance is not there in case of an LVDT. Okay, so this is the diagram of a commercially available LVDT. So here you have a shaft whose displacement is to be measured, and the primary and secondary terminals are taken out of here. Okay, so let's look into the actual working of this LVDT. Okay, so you have two secondaries that are electrically connected in phase opposition with one another, like here. Okay, so you would have, and now if you have this as ES1 and this as ES2, as the and that is being measured, EO is ES1 minus ES2. Okay, and as the core moves up and down, the magnitude of ES1 minus ES2 is going to change. Okay, and more precisely, if you say that ES1 is in phase with the input, okay, so, or in phase or almost in phase with input. So if the input has this, ES1 is going to lag a little bit, and so if you take this as the positive axis and this as the negative axis, okay, when the core is above the null position, the magnitude of ES1 would be greater than the magnitude of ES2. So you would have a output that is in phase with the input. Okay, however, whose magnitude will depend upon the distance from the null position. Okay, exactly at the null position it is going to be just a 0, because ES1 would be equal to ES2. Okay, and similarly when you go in the other direction, when you are somewhere here probably, then you would have the output being 180 degrees out of phase with the input. Okay, and of course again the magnitude will be proportional, or will be proportional to the displacement. Okay, so within this region it is going to be almost linear. Okay, now what will happen if you move the core a little too far? Okay, now if the core is moved little too far, let us say the core is moved into this position, okay, and is kept on moving further. So what is happening now is that the linkage with ES2 is completely 0. Okay, and the linkage with this S1 is also decreasing. Okay, because as this is decreasing, as this goes further, less and less of this first secondary, the S1 secondary is going to be linked, and so the magnitude of the effective magnitude of the output is also going to decrease. Okay, so there is some sort of a reversal here. So the magnitude of the output is going to decrease if the displacement is a little bit too large. So that brings a restriction on the range of operation. So the LVDT has to be operated within this linear range, and within this range the characteristics are quite linear. And note that we are not measuring L, okay, we are measuring a voltage V, though it's an AC voltage. So we are measuring a voltage. We will also measure whether it is in phase with the input or out of phase of the input. Okay, but what is to be noted is we are very confident, we are very competent in measuring voltages or currents, and measurement of inductance or resistance is basically only an indirect measurement. So, and that is quite a good advantage of an LVDT, that the output is going to be voltage and further conversion is really not necessary. Okay, when you have an LVDT for a rectilinear displacement, you also have an RVDT for rotary displacement, that is rotary variable differential transformer. Okay, and now here you have an asymmetric cam-shaped core. So when the core is in positions like this, okay, you have S1 dominating over S2, okay, and when you have the position somewhere like this, okay, then you have S2 is greater than S1, okay, and in fact but I made a mistake here. You don't take, you take only positions like this, okay, or like this. So here S1 is greater than S2, here S2 is greater than S1, and at the 0, this is, let us say, theta greater than 0, and this is theta less than 0. At theta equal to 0, you have S1 equal to S2, or ES1 is equal to ES2, I should say that. Okay, so that would mean that, like the case of an LVDT, the magnitude of the output will determine the magnitude of the angle. Okay, so if theta is greater than 0, okay, and so the whether you have a larger amplitude or whether you have a smaller amplitude will depend upon the magnitude of theta, and whether theta is greater than 0 or theta is less than 0, that will determine whether it is an in-phase signal or whether it is an out-of-phase signal. Okay, this is with theta greater than 0, this will be theta less than 0. Okay. Okay, now let's again revising the pros and cons for the for LVDT. It, because of its nature, it has quite a good linearity range. Okay, it will have good resolution, and because there is no, unlike the resistance measurement case or resistance transducers, you don't have a stepped wiper. Okay, you don't have, like a wire wound resistor, you don't have jumps in your output, so the resolution can be quite high, quite good. Okay, and since there is a primary which can be powered, okay, so basically you may not need an amplifier at all, the output can be read directly. And again, unlike the case of the wire wound resistive transducer, here this core is not touching any of these setups, any of the other coils at all. Okay, there is no electrical connection between the core, or there is no necessity of electrical connection between the moving part and the rest of the circuitry. So there is no friction. And since basically this is a transformer, the power loss is much less. So this LVDT as such will not consume much of a power except for the power that is required for the display. But on the other hand, LVDT does have some disadvantages also. Okay? Because it basically depends upon the magnetic coupling and the transformer effect. It is susceptible to stray magnetic fields. And since we want it to be sensitive to displacement, it also becomes sensitive to vibrations, okay, and other mechanical vibrations. And of course, since we are trying to relate the displacement to the actual voltage in the intermediate, we are making assumptions on what is the coupling, what is the mutual inductance in the primary and secondary. Okay, and those factors are in turn dependent upon, or in turn determined by the permeability of the material. Okay, so indirectly, and the permeability again of any material can again be dependent on temperature. Okay, so it is sensitive to stray magnetic fields, it's sensitive to vibration. There may be dependence on temperature, though the dependence on temperature can be mitigated to quite an extent by proper maintenance of the setups. Okay. The other disadvantage is that since it has to use the transformer effect again, it needs an AC supply and it can only give an AC input. It can't work on DC. And the third disadvantage that you have with an LVDT is that mechanically it is restricted by the mass of the core. So basically whatever displacement that you measure, whatever is the force that is causing this displacement, it should be able to move the core. Okay, so the mass of the core is going to put a lower limit on the force that is needed for the movement. So delicate forces, or small or if the force causing the displacement is going to be very less, then you need a very sensitive LVDT to be used for it. An LVDT whose core has much less mass. Okay, or in effect, core puts a limit on the force needed for the applied. And if when you want to measure the displacement, you have to assume that displacement is going to be changed. So there is a maximum frequency at which the input displacement can change. And for effectively catching the variation of the displacement, okay, and since we are not measuring the actual sinusoidal waveform, we are measuring only the magnitude of sinusoidal waveform. Enough number of cycles of this sinusoidal waveform should have passed when each of these displacement change happens. So it should mean that the supply frequency should be much greater than the input frequency or displacement change frequency. Okay, so that again puts a restriction on an electrical restriction on the supply frequency. Okay, so coming to the end, so you can refer to these chapters from A.K. Soni and Diobelin to have a better understanding of this topic. Okay, and thank you for your patience.